We have the pleasure to have Professor Jon Chapman from Oxford University. And his mini course will be about Ginsburg Landau vortices, the quantum side of our game.
Okay. So the PDF files that I'm going to use for the talk will be made available to you. So if you miss anything as I'm going along, then you can catch up there. It's also true that everybody is used to, undergraduates learn a little bit of fluid mechanics in their courses, whereas mathematicians very rarely come across superconductivity. So I thought I would start by introducing the basic phenomena of superconductivity in order to put the idea of superconducting vortices into context. So the lecture today is going to introduce you to the basics of superconductivity, the physical phenomena, the Ginsburg-Landau equations, and we'll get to vortices towards the end. And then tomorrow we'll look at systems of vortices in 2 dimensions, and then on Friday I'll look at some vortex filaments. So superconductivity was discovered back in 1911 in Leiden by Camerlinghonis. He'd succeeded in liquefying helium, and what he did was, after that, cool lots of things down and measure their properties. And he found that when a superconductor is cooled below its critical temperature, the resistivity drops sharply to 0. So it's a material that can carry an electric current without having an associated electric field. It's impossible to say the resistivity is actually 0, but they've had experiments with a loop of superconductor with a current, persistent current going around it for several years without any detectable loss of the current. So that puts an upper bound on the resistance of about 10 to the minus 8 that of copper. So to all intents and purposes, it's 0 resistivity. But that's only one of the hallmarks of superconductivity. So the other one is perhaps less well known in the popular literature, and that's perfect diamagnetism. And what that means is if you put a superconductor into a magnetic field, then it expels the magnetic field from its interior. So if I just had a perfect conductor, then that would behave sort of similarly in the sense that if I have a hypothetical perfect conductor and I move it into a magnetic field, then the moving magnetic field generates currents which would act to screen the interior. But a superconductor is different. If you put a superconductor above the critical temperature into a magnetic field, and then you reduce the temperature, when it goes superconducting, it expels the field. So it actually pushes it out. And this was discovered in 1933 by Meissner and Oxenfeld. It's now known as the Meissner Effect. I think Oxenfeld was the graduate student and Meissner was the supervisor, so he gets the credit. So the field is expelled from the interior except in thin boundary layers, and where there's a superconducting current which circulates on the boundary, which generates a field which exactly cancels that in the interior. So that's how it excludes the field. And the width of this layer is known as lambda. It's known as the penetration depth. And we'll see that appearing in the equations when we get to them. So you have perfect conductivity and you have perfect diamagnetism. And now the act of expelling this magnetic field costs you energy, which you gain back by being in the superconducting state. But that balance implies that if you keep putting stronger and stronger magnetic fields on, eventually it doesn't make sense to expel the field. It gets too energetically unfavorable. And so there's a critical magnetic field above which the superconductor reverts back to the normal state again. So in the popular literature, you usually hear about superconductivity as a temperature-controlled phenomenon, that if you cool something down, it becomes superconducting. But for the whole of these lectures, in fact, we're going to consider the isothermal state in which you fix the temperature and you control whether a material is superconducting or non-superconducting by the strength of the magnetic field that you apply. So if you apply a large magnetic field, the superconductor will go back to being a normal conductor. So this is the sort of phase diagram that you have. Here I've got temperature. Here I've got applied magnetic field. So at 0 magnetic field, so along this axis, if you're below the critical temperature, you're superconducting. And if you're above the critical temperature, you're non-superconducting or normally conducting. And then at any given temperature, there's a magnetic field, a critical magnetic field, which is a function of temperature. And if you apply a magnetic field above HC, you become normal again. if you're below HC, you're superconducting. So you get this region in field and temperature space where the superconducting state is favorable. So that's this left-hand graph. And on the right here, I'm showing the Meissner effect. So this is the average magnetic field inside the sample as a function of the magnetic field that I'm applying to it. So if I'm superconducting, the field is 0 on the inside. But when I cross the critical field, I become normally conducting again, and then the field penetrates, and the field inside the sample is just equal to the applied field. Now this is true for cylindrical samples in an axial magnetic field. And so why do I say that? That means that when the superconductor becomes superconducting, it doesn't distort the magnetic field. But if I have a transverse magnetic field, so a field which is not along the axis, then as the superconductor becomes superconducting and pushes the magnetic field out of its interior, then the field is distorted. And you can calculate what's the effect of the superconductor on the field. But it's a simple problem in magnetostatics. So with no applied currents, I've just got a uniform applied magnetic field. Then the curl of that magnetic field would be 0, and the divergence of that field would be 0. And that means I can write it as the gradient of a potential, which satisfies Laplace's equation. And the fact that there's no field on the interior gives me a Neumann boundary condition, and this just says that the field is uniform at infinity. So this I'm solving, I'm thinking of an axial, cylindrical superconductor with a transverse magnetic field, so I'm thinking in 2 dimensions here. So you can solve this problem trivially, and you can calculate what the magnetic field is, the total magnetic field due to the applied field and the distortion due to the fact that there's nothing on the inside. And when you do that, you find that the field at these points A and B is double the field at infinity. So that I apply a uniform field of value h naught at infinity, but if you calculate what it is at these points here, then you end up, where you can see from this term here, you end up finding that the field there is 2 times h naught. You get, this is the applied field, and this is the extra field due to the superconductor. So what that means is that if the applied field is half the critical field, then the field at these points A and B would be equal to the critical field. And so those points would no longer want to be superconducting. They'd want to be normally conducting again. But if the whole cylinder went normally conducting again, then the field would penetrate everywhere. You wouldn't have this distortion, and everything would be at h naught, which is less than the critical field. So in this situation, it doesn't make any sense for the superconductor to be superconducting, because then you have a field somewhere which is above critical. But it doesn't want to also be completely normal, because then you have a field everywhere which is below critical. So it has to do something else. And what it does is form some intermediate state. And so these blue and white regions represent some normally conducting material, some superconducting material. And here I've drawn this simple laminar pattern where you just have normal superconducting. But it has to do something like this in order that the field is less than the critical field everywhere where it's superconducting. And so this was a problem that people had looked at back in the 1930s and 40s. And in fact, if you do this experimentally, you can get some very intricate morphologies for these normal superconducting domain walls. And people had hypothesized this intermediate state. And then the question arose as to what should the length scale of these normal superconducting domains be? How big should these, you're going to have this sort of laminar structure. What sets the length scale for how wide a normal domain is and how wide a superconducting domain is? And in all these sorts of problems, the thing that sets that length scale is surface energy. That these things are going to have the same bulk energy, and if you want to keep refining and refining that pattern, well, the more you refine it, the more surface you introduce. And so the surface energy is what determines when it becomes not favorable to keep refining that structure. But nobody knew what the surface energy was for a normal superconducting transition region. And the Ginsburg-Landau theory was written down exactly to solve this problem. So it wasn't written down to do vortices or anything like that. It was written down to find out what's the surface energy of a normal superconducting transition region in order that they could predict what's the scale of this structure that you see. And they wrote their equations down in 1950, which was 7 years before the microscopic theory of superconductivity was written down. So it was a phenomenological theory. So a theory that was based on Landau's theory of second-order phase transitions, but modified in order to describe the phenomena that had been observed for superconductivity. And their main motivation, as I say, was to work out what was this surface energy for a normal superconducting transition region. All right, so that's the motivation for why they wanted to write their equations down. We'll see what the equations lead to later on. Before I can show you the Ginsburg-Landau energy and the Ginsburg-Landau equations, I have to just remind you what Maxwell's equations are. So I've got my notation. I've got an electric field is denoted by E, a magnetic field is H, and the current density is J. And here I've written it down allowing for a charge density rho. And so the divergence of the electric field is equal to the charge density. Epsilon is the permittivity. The divergence of the magnetic field is always equal to 0. There's no equivalent of charge for a magnetic field. There's no magnetic monopoles. The curl of the magnetic field gives me the electric current. And this is Faraday's law that says the curl of the electric field. So it says a moving magnetic field generates an electric field. And this is the way in which it does so. I'm neglecting displacement current, so we're not doing anything on the relativistic scale. And I'm going to assume that the permeability and the permittivity, so epsilon and mu, are constants. And later on, we're going to scale them out, and we'll tidy it all up so we can work with dimensionless equations. If I've got a normal region, so a normally conducting wire, then the relationship between the current and the electric field is just given by Ohm's law. So the current is proportional to the electric field, and the constant of proportionality is the conductivity, sigma. So the main reason for showing you these equations, I'm not going to use them much per se, but I sort of require you to look at them in order to understand what the magnetic vector potential is and why it arises. So the fact that I have the divergence of H is equal to 0 means that I can always write H as the curl of something. And that something I'm going to denote by A, and that's the magnetic vector potential. So that if you find H, if you defined by this equation, it automatically satisfies div H is equal to 0. And it's conventional to do this with the mu in there, so this is really, if you know Maxwell's equations, this is really B, not H. Okay, so that's A, that's a magnetic vector potential. I can then substitute that into Faraday's law, and then I've got a curl here, and this H becomes a curl as well. So this whole equation here ends up being written as the curl of E plus dA by dt is equal to 0. And so if the curl of something is equal to 0, then that something can be written as a gradient. And so this is the way that you can define the scalar potential or the electric potential, so that E plus dA by dt is equal to, it's conventional to put a minus sign in, so it's minus grad phi. So A here is only defined up to the addition of a gradient, because if I add a gradient to A, I don't change what its curl is. And once A is given, phi is only defined up to a function of t, because if I add a function of time to phi, I don't change what its gradient is. So neither of these is unique. You have a certain, it's called a gauge. You can choose the gauge of A, which means choosing what these functions are that you add on, which are a gradient in the case of A and a function of time in the case of phi. So that's a quick refresher on Maxwell's equations and magnetic vector potentials and scalar or electric potentials. I should say you can ask me questions as I go through, and if I go too fast or too slow, then please tell me as well. I'll attempt to modify. Okay, so Ginsburg-Landau theory is a steady state theory, as it was originally envisaged. And so in the steady state, there's no electric field. So H is constant, there's no dH by dt, therefore there's no electric field. So E is going to be equal to 0, and phi is also going to be equal to 0. And the premise behind the theory is that there's an order parameter, psi, which tells you to what degree the material is superconducting and to what degree it's not. So you can think of it as an order parameter so that the modulus squared represents the number or the number density of superconducting electron pairs. So if psi is mod psi squared is non-zero, that tells me there are some superconducting electrons there, and if it's equal to 0, it tells me there are no superconducting electrons there. But as Evelyn has already said, for the Gross-Pitaevsky equation, for the Ginsburg-Landau model of superconductivity, psi is not just a real scalar, but ends up being a complex scalar. So you have a complex order parameter. So this was a strange generalization of Landau's second-order theory of phase transitions. And the need for this parameter to be complex really arises because of the quantum mechanical nature of superconductivity. So it's the fact, you can think of it as an average macroscopic wave function for the superconducting electrons. And later it was derived from the microscopic theory. You could perform some manipulations and sort of deduce the Ginsburg-Landau theory, and that sort of justified the need for this order parameter to be complex valued. But the way I always think of it is that the modulus tells me how many superconducting electrons there are, and with superconductors, the electrons are all sort of in phase, and so their wave functions add up instead of cancelling out, and that psi ends up being the sort of macroscopic wave function for the superconducting electrons. So that's the first step. Then the second step is to look at the free energy density, Helmholtz free energy density, and think of this as doing a power series expansion in this order parameter. So the free energy density depends on how many electrons there are, superconducting electrons, and so you can write this as a power series in the number density of electrons, which is mod psi squared, and then the theory sort of valid close to the critical temperature at which you can truncate this series after the second term. We'll see why you need to take two terms here in a second. And the idea is that if you're below the critical temperature, then the minimum of this function should be psi is equal to 0. Sorry, if you're above the critical temperature, the minimum should be psi is 0 so that you don't have any superconducting electrons. But if you reduce the temperature below the critical temperature, then the minimum of this function should give you a positive value for psi. So that if you minimize this free energy, it tells you that above the critical temperature, the material should be normally conducting, but below the critical temperature, it should be superconducting. And so I have a picture of that. So if you, above the critical temperature, you want it to look like this. So this is the modulus of psi squared. Of course, because it's complex, really, if you think of this as the Argand diagram, so this is the real part and this is the imaginary part, it's really a bowl rather than it sort of sits in 2D rather than 1D. And so this is if the temperature is above the critical temperature. And then if the temperature is reduced below the critical temperature, then you want the function to look like this so that you have a minimum value here, which is at a non-zero value of mod psi squared. And of course, this is really just a cross-section of this sort of Mexican hat, where the phase of psi is not determined because the energy is only a function of the modulus of psi. So in order to generate something that looks like this, you want these coefficients here have to be chosen so that B is positive, so it always goes up for large psi, And then you want A to be positive if the temperature is above critical, and you want A to be negative if the temperature is below critical. And that generates these extra wells that are away from psi is equal to 0. So A is a function that goes through 0 at the critical temperature. And then when you do that and you minimize this energy for temperatures below critical, you find that the value you get for mod psi squared is minus A over B. Remember, A is negative, so that's a positive value. So that's sort of Landau's general theory of second-order phase transitions, is to do this sort of expansion of the free energy, have the coefficient A to go through 0 at the critical temperature, and then the minimizer of this function switches from being at psi is equal to 0 to psi is equal to some positive value. So that would work if you didn't have a magnetic field. So now you've got to start taking that energy and you've got to add all the other bits onto it that you need in a real situation with a magnetic field. So the first thing you have to add is the magnetic field energy density. So that's just proportional to the square of the modulus of the magnetic field. And then you have to allow for the possibility of gradients in the order parameter, and you want to penalize gradients. And usually what you do in order to penalize gradients is you add some term which is just proportional to the square of the gradient. And then whenever there's a gradient in psi, there's going to be a positive energy, so it's going to penalize the gradients. So the tricky thing about the Ginsburg-Landau model of superconductivity by comparison to the general theory of second-order phase transitions is that, well, so far we haven't included the interaction with the magnetic field between the order parameter and the magnetic field. And we also have to make sure that whatever energy we get is gauge invariant, in the sense that if I add a gradient of a function to the vector potential A, then I shouldn't change the energy. I'm allowed to change the phase of psi, but it shouldn't change the modulus of psi. And so what Ginsburg and Landau wrote down was not a term like this, but a term like this. And so you change this gradient into a sort of gauge invariant form, where it involves not just the gradient of psi, but also this vector potential A times by psi. And this is really by analogy with quantum mechanics. This is what you would have for an electron in quantum mechanics in the presence of a magnetic field. But here I'm just going to do what they did in their original paper and postulate that this is the sort of surface energy that you have to write down if you want it to be gauge invariant. It turns out that the constants that you put in here actually don't really make much difference because they all end up getting scaled out in the end, but it's traditional to think of this as the charge on a superconducting charge carrier, and superconductivity is to do with pairs of electrons. So you traditionally think of this as being twice the electronic charge. And similarly, the mass here is sort of arbitrary, but it's traditional to think of that as being twice the mass of an electron. Another way to interpret that energy is to split it into two components. So if I decompose this order parameter into a modulus and a phase, so I'm going to call the modulus F and the phase I'm going to call chi, then you can write that energy as two terms, one of which is just the gradient of the modulus squared, and then the second involves the gradient of the phase combined with this magnetic vector potential. And then you can sort of see, well, what do these two correspond to physically? So this first one is again just penalizing curvature in the level sets of F. So it's penalizing gradients in the modulus. And the second one you can think of as a kinetic energy, if you like, of the superconducting electrons. That we'll see later that the current, well, in fact, Evelyn has already shown you that the current for Gross-Peteevsky is proportional to the gradient of phi, gradient of chi in my case, with an F squared out the front. in a magnetic field, I would also have the potential would be in here. And so this tells me that this term here is really the velocity of the superconducting electrons. And so this term here is really F squared is what Eveline called rho, the density. So this is density multiplied by velocity squared. So this is, you can think of this as the kinetic energy of the superconducting electrons. All right, so this, when you put all those bits together, this is what you end up with. So the free energy is whatever background free energy I've got. I've got this power series expansion in mod psi squared. I've got this gradient term, which is going to penalize gradients in psi. And I've got the magnetic field energy density. And it's been constructed so that it's gauge invariant. So if I add the gradient of a function to A, all I do is modify the phase of the order parameter. Phase is not a physical quantity, so that doesn't change anything that can be physically measured. So this is Helmholtz free energy density. In the presence of a magnetic field, if I want to work out what the Gibbs free energy density is, the difference between those two is the work done by the EMF induced by the applied field. And what that means is I've got to add one extra term, which is the magnetic field dot the applied field. And this is how the applied field gets into the free energy density. So instead of just having this mu mod h squared, I end up with an h dot h naught, where h naught is the applied field. And so this energy density has been constructed to be valid in the superconducting material, but in fact I could write down exactly the same sort of energy density outside the superconducting material. I just wouldn't have any psi. There'd be no possibility of having any superconducting electrons, so I wouldn't have any of these terms, and the only bit that I would have is the magnetic field energy density. But I could perfectly well do that, and then I can minimize the energy not just over the superconductor, but also over the external region as well. And that's because when the superconductor doesn't allow the field into its interior, we've seen it modifies the external field, and that costs it energy, so you have to worry about that. So having constructed this energy, the basic thermodynamic postulate of the Ginsburg-Landau theory is that this guy should be minimized. So in steady state, the integral of the Gibbs free energy in the presence of a magnetic field should be minimized.
If I understand it correctly, most of this is basically, this physical ground is more phenomenological. Right?
This is all phenomenological, yeah. So it was later derived from the BCS theory. So from the microscopic theory, for particular types of superconductors with particular band gaps and things, you could derive similar sort of equations. But the original theory was a phenomenological theory.
And then in order to basically move from inside the superconductor to outside to have the same function, is it possible, say, to multiply by some kind of like another sort of like cutoff function, which is like 1 inside and 0 outside, or basically to set the thing in the neighborhood, in the boundary, such that basically takes a variation or a consideration or not?
Certainly you could, yes. So at the moment, what I've just said is that I'm going to write this energy down. I'm going to integrate this thing over the superconductor, and I'm just going to integrate these two guys over the exterior region. I could do that just by multiplying this by the characteristic function of the superconductor.
And that characteristic takes something smoother, like we've done sometimes in some kind of Helium or something like that.
Yes, you could.
When you have interface between things, that it's not really transition, it's not really that delta function, but rather there's something smoother.
Yeah, you could certainly do that. And in fact, you do get a phenomena of surface, a surface effect where even if you put two materials up against each other, it's not a sharp transition, that you get a few superconducting electrons in the non-superconductor and vice versa. Okay, so before I go and write down the minimizer in general, let's just see how the theory has developed so far sort of satisfies the phenomena that we've described so far. So if I have a non-superconducting material, then I put psi is equal to 0, and I can evaluate what this free energy is. And the only bit that I have then is the magnetic field energy, and that is minimized just by saying the field penetrates. So the field inside the superconductor is equal to the applied field. And if you do that, this is the value that you get for the Gibbs free energy. So that's if it's not superconducting. If it is superconducting, then I want to put psi as minus A over B, and the field is expelled, so I have H is equal to 0. And then this is the value that you get for the Gibbs free energy. So here you see directly this competition that I mentioned earlier between excluding the magnetic field costs you energy, because you've had to pay this minus a half mu h squared is not in here. So I've had to pay that in order to go superconducting, but I've gained back a minus a squared over 2b by being in the superconducting state. So I have a competition between these two different terms, and if the applied field is low, then this is going to be the lower energy if h naught is small. But if h naught is big, then this term here ends up being bigger than this term here, and it's not worth being superconducting. So from this you can calculate what's the applied magnetic field at which it becomes energetically favorable not to be superconducting anymore. And you do that just by equating these two terms, and you find that gives you this expression for the critical field. And if you, this is isothermal, but you could do it at any temperature, so you can have temperature in here as a parameter. And you see the critical field will go to 0 at the critical temperature, because A goes to 0 at the critical temperature. So the equations describing the critical field, the phenomenology in the right sort of way. Okay, so for a more general situation, if I have a superconductor which occupies some region of R cubed, then in order to minimize this energy, I have to use the calculus of variations, and you're going to get the Euler-Lagrange equations associated with variations of psi and A. So what am I minimizing over? I'm minimizing over all possible values of psi and all possible values of the magnetic vector potential A. So if you minimize with respect to psi, or this is the equation that you would get by minimizing with respect to the conjugate of psi, which is psi star, you get this equation, and then you minimize with respect to vector potential, and you get this equation. And those two are what you would get inside the superconductor, and then outside the superconductor, you only have the magnetic field term, so you don't have anything to do with psi. So you get curl squared of the vector potential is equal to, well, it's the curl of the applied field. So the applied field outside the superconductor, if it's a uniform field, it won't have any curl. But curl of H naught is really the applied current. So if you are generating a field by having a solenoid or whatever, then this would be non-zero inside the solenoid. And so this term here is exactly an expression for the superconducting current. So if you remember that magnetic field H is given by the curl of A, and then the supercurrent J is given by the curl of H. And so curl squared of A, it's the notation is not quite right. It's the curl operator is squared and then applied to A. So it's curl of A. So curl of A is equal to the current. So this is the current outside and this is the current inside. So this is the expression for the supercurrent. Psi star here, as I said, is the complex conjugate. And then associated with the minimization, you'd also get some natural boundary conditions. And from the minimization of a psi, you get this boundary condition. And this basically says that no supercurrent goes through the boundary. And from the minimization over A, you get this boundary condition where that's the jump in curl A cross N. So curl A is the magnetic field. So curl A cross N is the tangential component of the magnetic field. So it says the tangential component of the magnetic field is continuous. And then you find this just says that the magnetic field tends to the applied magnetic field when you go to infinity. So often these equations are written down for a superconductor occupying the whole of space, and in which case you don't have to worry about these boundary conditions, and that we're going to do a bit of that later on. But this is what you would get in general if you have a superconducting domain and you have some region outside of that domain as well. Okay, and they're a bit messy at the moment because I've left all the constants and things in so that they're all dimensional. But I'm going to tidy them up by non-dimensionalizing in a minute. But the reason I've left them dimensional was so you could see these two length scales. So I've got an equation for psi, and both equations involve psi and A. But you can sort of think of this as being, this has got two derivatives on psi, so you can think of this as being the equation for psi, and this has got two derivatives on A, so you can think of this as being the equation for A. And if you look at the second derivative term here, and you compare it to this term, which is linear in psi on the right-hand side, you can see that you've got a length scale associated with this equation. So here I've got an h squared over 4m times second derivative of psi is equal to A. So that gives you exponentials, it gives you a length scale, and that length scale is just h over 2 times the root of ma. And that's the length scale over which psi varies. It's the length scale associated with that equation. And that tends to be known as the coherence length, thinking of the coherence between the wave functions for the individual superconducting electrons. And it's usually given the symbol psi. So you get one length scale from the psi equation. And then if you look at the same equation, do the same thing on this equation here. So you look at the curl squared of A on this side, and you look at the A term on the right. So I've got a length scale associated with those two terms. If I balance them, then that tells me the length scale over which A varies, and that ends up being this combination of parameters here. So you've got two equations, an equation for psi and an equation for A, and each of those has got a length scale in it. And the length scale for A is the length scale over which the magnetic field varies, and that's given the symbol lambda, and I've already said this is known as the penetration depth. And the ratio of these two length scales is a key parameter which tells you how the superconductor is going to behave. It's a material parameter. Lambda over psi is known as kappa, the Ginsburg-Landau parameter. And we'll see a bit of kappa throughout the lecture course. So I can use these two length scales in order to non-dimensionalize the equations. I have to choose scales for psi and scales for A, and I have to choose a length to choose as my length scale. So I have to either choose psi as a length scale or I have to choose lambda as a length scale. And it's usual to use lambda, so I'm going to use lambda for the time being, but later on I might switch and use psi. So length is now going to be scaled with the penetration depth, so I'm going to be on the natural length scale for variations in the magnetic field. Psi, we've seen that in the absence of a magnetic field, then psi takes the value root A over B, so that's the natural scale for variation in psi. And once you know those two, you look at the equations, and that tells you what the natural scale is for H, which is basically the scale of the critical field. And from the fact that curl of A is equal to H, A is just lambda times the scale for H. So through the non-dimensionalization, I can tidy the equations up, get rid of all the constants, and you get this nice clean form with the Ginsburg-Landau equations. So now all the E's and the M's and the Planck's constant and all that sort of stuff disappears, and the only parameter that you've got left in the equation is this kappa, this Ginsburg-Landau parameter. And it appears in front of any derivative of psi, because I had a length scale for variations of psi, which was psi, the coherence length, and I had a length scale for variations of A, which was lambda, the penetration depth. So now if I'm scaling length with the penetration depth, the length scale for variation of psi in these equations is the ratio of those two lengths, which ends up being kappa. So now in these equations, the order parameter psi varies on the length scale of kappa, of 1 over kappa. And A varies on an order 1 length scale. And if you tidy the boundary conditions, you just get the same conditions as we had before without any of the constants in them. And if you work out what's the critical field in these units, then you find, based on this scaling and what we had for the critical field before, you get this root 2 here. So 1 over root 2 is the critical field in these non-dimensional units. And the corresponding Ginsburg-Landau free energy has also been tidied up a little bit. So the power series expansion in terms of mod psi squared has now just become the 1 minus psi squared all squared. Again, I've got the 1 over kappa in front of the gradient of psi here. So this is similar to the Gross-Pitaevsky equation that we saw before lunch, apart from if you cross the magnetic vector potential out of here, then here's the cubic nonlinearity in psi that appears also in the Gross-Pitaevsky equation. This is steady state. Okay, so there's a lot of work that Ginsburg and Landau have done to get to these equations, but they're now in a position to say, all right, we've got this whole theory. Can we go back and say, what is the surface energy of a normal superconducting interface, having got this far? Before I do that, just mention that they're still gauge invariant, even in this non-dimensional form. So now when you add any gradient to A, you just got to change the phase of the order parameter psi, just with the kappa goes in there. And in fact, you can take advantage of this gauge invariance to write the equations in terms of real variables instead of these complex variables. So if you do real and imaginary parts of the first equation for psi, and you write psi as a modulus times e to the I chi, modulus and phase, then you end up getting this equation for the modulus, where the Q here is basically like A, but it's got the gradient of the order parameter subtracted from it. So this Q is invariant under this phase transformation. That whatever you add to A, you add the same thing to this chi, so that Q ends up being invariant. So it's a sort of invariant potential, this Q. So in fact, you get a nice, much simpler looking equation for the modulus F. The imaginary part of that equation for psi ends up telling you the div of F squared Q is 0. In fact, that follows automatically from the third equation if I take the divergence of this equation, because the divergence of curl is 0. So this is now the equation for the supercurrent. So curl of A is equal to curl of Q. So curl squared of Q is equal to minus J. So this is minus the supercurrent is equal to F squared Q. So the supercurrent is proportional to F squared and proportional to this gauge invariant potential. And the boundary conditions also tidy up a little bit in this case. You have a Neumann boundary condition on F. You have no normal component of Q. And then again, you have continuity of the curl of the tangential component of magnetic field. And Q goes to H naught infinity. So sometimes it's useful to use this real version of the equations. And I'll come back to this quite a lot, actually, tomorrow and Friday. So far, I'm presenting everything in full 3 gory dimensions. This equations simplify a lot if you go into 2 dimensions. And in particular, there's a 2-dimensional situation of a cylinder of superconductor with an axial magnetic field. And if the field goes along the axis, so if the field is only in the z direction, and it's allowed to depend on x, y, and t, and correspondingly the magnetic potential, you only have to use two components, the first two components of it. Then the advantage of this is that outside the superconductor, if you've got a field that is unidirectional like that, then when you apply the Maxwell's equation, so I've got no current outside, curl H is equal to 0. I always have div H is equal to 0. Then that just tells me that the gradient of this function is 0. So that tells me whatever I apply at infinity, I can just bring it into the edge of the superconductor. So I don't have to worry about the exterior region at all. The applied field can be applied directly on the boundary of the superconductor. So I don't have any distortion of the magnetic field outside. And so this two-dimensional situation is actually very commonly studied for that reason, that it's very easy to just apply a magnetic field to the boundary. And it's often much simpler than the general case. So again, in fact, most of tomorrow's lecture will be in this two-dimensional situation. Okay, so finally, the normal superconducting interface. I want a transition region between normal stuff over here and superconducting stuff over here. And I can use the Ginsburg-Landau equations to solve for such a transition region. So if I take the interface, if I take this to be the x direction, I'm going to take the magnetic field to be in the z direction, and that means the potential can be in the y direction, and then you just get that the field is just the derivative of potential. Then it turns out for this one-dimensional situation, the order parameter turns out to be real, and you just get this very simple pair of equations for the vector potential and the real scalar order parameter, where prime is just d by dx. And these guys form a Hamiltonian system, so the Hamiltonian is constant, so there's a first integral of the equations even. And the boundary conditions that I want, well, I want it to be superconducting at one end at minus infinity, which is that side for me, but it's probably that side for you. So superconducting means no magnetic field, A is 0, and the maximum number of superconducting electrons, which in this normalized case means psi goes to 1. So I need this at one end, and at the other end, I want it to be normal, so psi goes to 0, and the derivative of the potential should go to whatever the applied field is, whatever the field is in the normal region. Now, it turns out that these equations only admit a solution if the field on the normal side is equal to the critical field. That if you've got a transition between a normal region and a superconducting region, you can only have a steady transition if the field is exactly critical. And you can see that by, if you apply these boundary conditions, that tells you what this constant is. It turns out to be minus a half. If you put psi as 1 and you get minus a half from these, and then these guys all give you 0. So this constant is minus a half. And now you look at what happens when psi goes to 0. So this term, this term, this term, and this term disappear. So you get minus a prime squared is minus a half. So that tells you a prime is 1 over root 2.
You did the scaling originally until you get something with the Ginsburg-Landau parameter. Was the domain of the superconducting domain rescaled?
So good question. So at the moment, the superconducting.
The reason I'm asking that because I would like to see where is the boundary of the superconducting domain in this setting, at least one dimension.
So in this case, I'm imagining that the superconductor occupies the whole of space, which is another way of saying that I want it to be much bigger than this interface. And so it's gone off to infinity. But we're going to come back later in the course as I've rescaled onto the penetration depth, which is basically, if I keep a finite superconductor in this scaling, I'm saying it's pretty small actually, because the superconductor is also the same size as the penetration depth. And that's another argument that says when you're on this scale, it's all right to say you've got an infinite superconductor, because infinite is actually not that big in that case. But yes, so thank you. So here I'm thinking of the superconductor occupying the whole of space, which is another way of saying that I want this this transition layer, which is varying on the scale of the penetration depth, to actually just be much smaller than the overall size of the superconductor. Okay, so H is equal to Hc on the normal side. So that tells you that you can only have this stationary transition if the field in the normal region is equal to critical, so that the bulk energies at plus and minus infinity are the same. All right, so this is the description of what a transition layer looks like in terms of what a psi and A as a function of x. But what's the energy of the transition layer? So to do that, I have to say, well, having got this this solution to these equations, now let me stick it back into the Ginsburg-Landau energy and see, just do the integral. So what I want to calculate is actually the difference between the energy of the transition region over the energy that I would have if I didn't have a transition region. So if either I was all superconducting or all normal, and because I'm at the critical field, those two energies are the same, so it doesn't matter which one I choose. So this is the energy of the transition region, and I subtract off what energy I would get if it was just all normal. And I do that so that I get a finite energy, which just tells me what's the excess energy of having this interface. So this is the Ginsburg-Landau energy minus this normal bit, which has just affected what the field energy was at the end. And then by using that first integral and messing about with the equations a bit, you can simplify this down a little bit to this, but you still got to then go and actually do this integral. But it is possible to prove that this value you get for this surface energy is positive, but not always. So the Ginsburg and Landau's idea in their original paper was just to show that this energy was positive. And it turns out it's only positive for certain values of this Ginsburg-Landau parameter. So if, in particular, this parameter has to be less than 1 over root 2 for this surface energy to be positive. And then surface energy is equal to 0 if kappa is 1 over root 2. And if kappa is greater than 1 over root 2, then this surface energy is negative. So they sort of half succeeded in their goal in writing this paper. Their goal was to derive this surface energy and prove that it was positive. And they found out that, it's not always positive. And in fact, at the time, they said, well, obviously, superconductors with kappa greater than 1 over root 2 it's not physical. You can never have negative surface energies. So they said that there must not be any materials that have kappa greater than 1 over root 2. And the physical situation must correspond to kappa being less than 1 over root 2. It turns out that that's not true. That there are materials with kappa greater than 1 over root 2, and they do indeed have a negative surface energy for a normal superconducting transition region. And so normally, if you have a negative surface energy, you would say you want to make as much surface as possible, and you would have infinitely fine structures, and the whole thing would be ill-posed. And what saves you in this case is the quantum nature of superconductivity, or in this particular example, it's the fact that you have a complex order parameter. And so you have quantization of magnetic field, which we'll come on to. And that stops you from having an infinitely fine structure. You can get down to a normal region, which is a point, but you can't get smaller than that. And then you find that the magnetic field varies on this penetration depth away from that point. So you get very fine structures, but they're not infinitely fine. And these were first looked at by Abrikosov a little bit later. He published his paper in 1957. The story is that Landau told him that it was obviously wrong and that he shouldn't publish it. And then eventually Landau relented and let him publish the fact that this analysis on these materials with kappa greater than 1 over root 2. So in fact, it's one of the great, even though Ginsburg and Landau didn't sort of acknowledge it at the time, it's one of the great successes of the theory that it sort of allowed for type 2 superconductors about 10 years before, 10, 15 years before they were actually discovered and proved to exist. And it's even worse. It seemed like it was unphysical at the time, so it seemed like it was a bad theory, but actually being able to predict something which is then later discovered is the hallmark of very good theory. So it's one of the great successes of the theory that it predicted the existence of these type 2 superconductors. So I should say that, so we now say that if a material has got kappa less than 1 over root 2, it's type 1, and if a material has kappa greater than 1 over root 2, then it's known as a type 2 superconductor. And in fact, almost all technological applications of superconductivity involve type 2 superconductors. And so they're far, far more important than type 1 superconductors. But the negative surface energy of type 2 superconductors means that you get a very different morphology for this mixed state where you want to make as much interface as possible. So I drew a simple sort of laminar structure for the intermediate state of a type 1 superconductor. The way the magnetic field penetrates a type 2 superconductor is by making a lot of very small normal regions, as small as they can possibly be. And it's these that we now call, so you think of them as flux tubes, if you like, but we now call them vortices because of the supercurrent which is associated with these, with a single quantum of magnetic flux. So a type 2 superconductor in this mixed state where it has a lot of very small normal regions is the subject of this lecture course. Okay, so why can they not be arbitrarily small? I keep talking about quantization, and it all, again, comes down to having a complex order parameter. So if I look again at this equation for the electric current, so I've got the electric current's the curl of the magnetic field, which is the curl of the vector potential. And that's the Ginsburg-Landau equation tells you that that's equal to minus f squared q. So f is the modulus of the order parameter, and q is this gauge invariant potential. So now, suppose I have a hole in my superconductor. A hole can be, can be any normal region, or it could be a physical hole in the material. And suppose I choose a closed curve that encircles this hole. And I want to integrate this expression along this closed curve C. So I want to choose this curve so that the modulus of psi is never 0 anywhere on it. So it never goes through a normal region. So then if you just divide this equation by the f squared and integrate, you find that this integral of 1 over mod psi squared j around this curve is just equal to the integral of q around the curve. And then if you remember the definition of q, so q is a minus 1 over kappa grad chi. So on this curve here, I can use Stokes' theorem to turn the integral of a around c into the integral of the curl of a over the surface, which is the interior of that curve. So this is, and the curl of A is just equal to the magnetic field. So this is the magnetic field contained inside that curve, so throughout this whole region. And then the integral of a gradient around a closed curve is, it would be 0, but in fact this phase is not required to be single valued. The phase, as I go around this curve, can change by an integer multiple of 2 pi, because only psi is required to be single valued, but the phase of psi can vary by an integer multiple of 2 pi. So here I get an integer multiple of 2 pi over kappa from this phase. So if I rearrange this equation, so I bring the j onto this side and take the n over kappa onto the other side, you find that this integral is quantized in multiples of 2 pi over kappa, where n is sort of the winding number of the phase as you go around this curve. So this left-hand side is, well, it's almost the flux through this curve C. That's what this bit is, but it's got this extra bit due to the supercurrent. So it's usually known as the fluxoid, this whole thing. And so the fluxoid around any curve is quantized in integer multiples of 2 pi over kappa. The other way to do it is to say, well, let me take this C so far inside the superconductor that J has gone to 0. So you remember the currents all flow in a thin layer around the edge of the order of the penetration depth. So once I get far enough inside, this term actually goes to 0. And then the magnetic field is quantized in units of 2 pi over kappa. And that sort of says the magnetic field around this hole is quantized if you include the little bit of magnetic field that penetrates by the surface. So this is actually an effect which has got technological applications. So there's a device called a SQUID, which is a superconducting quantum interference device, which uses exactly this idea. And it's a way of measuring very accurately small changes in magnetic field, because you have a loop of superconducting material. And you can really tell so you know that the amount of magnetic field inside is quantized in units of 2 pi over kappa, and you can really tell when this n changes by measuring the current in the wire. And because 2 pi over kappa is really quite small, it's a way of getting very accurate magnetic field measurements.
So is this implemented technologically?
Yeah.
So, I mean, at the very beginning, this story, the way I understand it from you, and I know it, is that superconducting material was produced by helium at very low temperature. Is there no other superconducting material than helium at low temperature, so that you can really create such a device to be practical, or do you need to have so low temperature that...
Usually, they do still use helium, because so there are some materials that will superconduct at liquid nitrogen temperatures, and they're cheaper, but it's a trade-off that the superconductor is less good, but the cooling is cheaper. And it's a trade-off as to, somebody once told me when they tried to compare the cost of liquid helium versus liquid nitrogen, they said liquid nitrogen is about the same price as beer, and liquid helium is about the same price as good malt whiskey. So that's the sort of relative difference in price. So in fact, most of the technological applications of superconductivity use helium, because it's expensive, but it's not that expensive. You've got to get it cold, and then you just got to keep it cold. But that works because you've got small-scale devices. So NMR machines in hospitals all use liquid helium, but it's all relatively small. If you want to make a train that goes a long way, then liquid helium gets very expensive because you've got to do a lot of it. So that's when you want to go to liquid nitrogen. So I described this flux quantization as though we had a hole in the superconductor, but it would equally work if you had a normal region and you just integrate around it. And what that says is that the flux through a normal region cannot be arbitrarily small. It has to be quantized in units of 2 pi over kappa. So you cannot have arbitrarily small normal regions. And this is what sets the scale for this mixed state of type 2 superconductors. In fact, fluxoid quantization can also be used to explain this experiment I mentioned right at the beginning about the persistent currents in a superconducting loop. That, so if you have a current going around a wire, the field that it generates inside the wire is not allowed to slowly decay. It can only jump by quanta. So if it wants to decay, it has to decay in units of 2 pi over kappa. So for the flux to go down, it has to reduce the value of n by 1. And in order to do that, so I said the flux quantum is small, but it's still, Avogadro's number is very big. And so in order to reduce the magnetic field by 1 quantum of flux, you would require about 10 to the 20 electrons to change their state. And that's the sort of jump that just doesn't happen. And so this is what says that quantum jumps are not going to cause the decay of a superconducting current circulating in a loop, even though it's not the most energetically favorable state. So it would have a higher energy than having no current at all. But it's impossible to reach the no current state because of this quantization. Okay, so I showed you the phase diagram earlier without sort of saying that I was limiting myself to type 1 superconductors. But now we've heard about type 2 superconductors, I can show you how that diagram changes when you have this negative surface energy. So this is the diagram where before we've got applied magnetic field and we've got temperature. And what we had before was one curve here where if I was below the critical field, I'm superconducting, and if I'm above the critical field, then I'm normal. What we've got this time is it splits into 2 critical fields. So I have a lower critical field. If the magnetic field is still sufficiently small, it's still better to be superconducting. But then when you cross this first critical field, this HC1, you find that you want to go into some mixed state where you have a mixture of bits of superconducting and bits of normal material. And that's because you've got this negative surface energy. You want to make as much surface as possible. But still, if you apply a strong enough magnetic field, then eventually it becomes preferable to go back normal again. So you have an upper critical field or an HC2. So you have now, instead of just 2 states, you have 3 states. You have normal, you have superconducting, and you have mixed. And this is different to this intermediate state of type 1 superconductors where it was all to do with the geometry and the distortion of the external field. This happens even if there's no distortion of the external field. It's all to do with this negative surface energy. And if you look at the average field inside the superconductor as a function of the field that you apply, well, you still have a complete Meissner effect if you're less than HC1. So you've still got no field inside the sample there. And you've still got full penetration if you're bigger than HC2, if you're normal. But if you're in between these 2 fields, you sort of have a partial penetration of the magnetic field. So there's some magnetic field in the sample, but it's not as big as the applied field. So you have a sort of partial exclusion. And in fact, almost all technological applications of superconductivity involve type 2 superconductors in this mixed state. So it's the most interesting aspect of, it's one of the interesting aspects of superconductivity from the mathematical point of view, but it's also the most relevant from a technological point of view. And that's because this magnetic field HC2 is typically much bigger than the thermodynamic critical field HC. So that enables you to have some remnant of superconductivity at much higher fields. So that if you have the superconducting magnets that are in MRI machines in every hospital are superconductors in the type 2 state used to generate a strong magnetic field. And this is what the phase of a superconductor now looks like as a function of, so for fixed temperature, as a function of magnetic field and Ginsburg Landau parameter kappa. So type 1 superconductors lie to the left of 1 over root 2, and you're superconducting if the field is small enough, and you're normal if the field is too big. And then at this critical value 1 over root 2, when you get to type 2 superconductors, this one field splits into 2, and you have this extra mixed state which exists between the normal and the superconducting states. All right, and this is what the profile of the order parameter typically looks like in the mixed state. This is up close to the upper critical field. So each one of these is a 0 of the order parameter. This is the modulus of the order parameter that I'm showing you. So this is the 0 of the order parameter. These curves here would also be, so they're the level curves of the order parameter, but as we saw this morning, that's also the direction of the electric current. And so the electric current is circling around each one of these. So you have a 0 of the order parameter. A magnetic field would be localized in this region, and associated with that field, there'd be a circulating current. So each one of these would be a vortex, And this is the partial penetration of the magnetic field happens through this very fine scale structure, but it's not infinitely fine because the length scale here, well, the length scale for the variation of F here is set by this coherence length. So it's 1/kappa in these units. And what you find up near HC2, up near the upper critical field, is that you get this hexagonal array of vortices. You get this very regular structure. But if you reduce the magnetic field, then these things will gradually separate, and then it makes sense to look at an isolated vortex. So you can look at just one vortex on its own. So what does a vortex solution look like? So again, this parallels exactly what we saw this morning, where we didn't have a magnetic field, so we didn't have a vector potential, but the equations are very similar if you just put A is equal to 0. So here my superconducting order parameter would be written in terms of a modulus and a phase, and for a single isolated vortex in an infinite domain, then the phase is some multiple of theta, the polar angle, where n is the winding number, it's the degree of the vortex, it's the number of quanta it contains. And the modulus will be just a function of the radial coordinate. So F would just be a function of R. So this is what the order parameter looks like. Now, the vector potential, the natural one to choose in this situation is, again, a vector potential where the modulus of the potential only depends on radial distance. And it turns out the direction of the potential is then, again, in the azimuthal direction, so in the theta direction. So you can make this ansatz for a solution, and you stick it into the equations, and you find that it works, providing that F and A satisfy this pair of ordinary differential equations. And the boundary conditions that you would want, so you want the material to become superconducting again at infinity, so you have F goes to 1 and A goes to 0 as R goes to infinity. And then you want F and A to be bounded at the origin, which is enough to fix you a unique solution to these equations. The supercurrent is given by curl of H, and which is this guy here, so that ends up being minus F squared times A minus N over kappa R, and again, it's in the azimuthal direction, so in the theta direction. And that shows you that you're getting the vortex. This is why these are called vortices. And the total magnetic field, if I integrate the magnetic field over the whole space, then for this particular solution, you find that you have n quanta, where this n is the degree of the vortex, and one quantum we've seen is 2 pi over kappa. So if you integrate H over the whole domain, you find you get 2 pi n over kappa out of this. So this is sort of the building block of the whole theory of vortices. It's a single, isolated, rectilinear vortex solution. And this is what it looks like. So this is the order parameter would be 1 at infinity. It's radial, and it dips down to 0 at a point. And there really is a sharp cusp there, because remember, I'm taking the modulus of the complex function psi. So psi is regular at the origin, but F is not as a function of x and y. The magnetic field decays to 0 at infinity, but it raises up into a bump at the center of the vortex associated with this normal region. And that's the reason that, so in the physics literature, these are often known as flux tubes. If you think of this as a cylinder, then this is a tube of material which is carrying magnetic field. So there's magnetic field along the axis of this line. And then this is the supercurrent is going around here. These are the level curves of supercurrent. And so that shows you the vortex nature of the solution. Now, a nice expansion to do, or a nice approximation to do, which Evelyn sort of alluded to this morning, is that I have these two length scales. I've got the length scale for the variation of the order parameter, and I've got the length scale of the variation for the magnetic field. And there are quite a lot of materials in which the ratio of these length scales, which is this kappa, is actually quite large. And in fact, the bigger kappa is, the better from a technological point of view, because you get to higher magnetic fields. And so it makes sense to look at an expansion in terms of large kappa. And if you do that, you find that in this picture, you get a separation of length scales. So the length scale over which this f varies is 1 over kappa, and the length scale over which h varies is 1. So if I let kappa go to infinity, then this picture shrinks, and you find that f is equal to 1, apart from when you get very close to the origin. So you end up with two expansions to do. You have what you call an outer expansion, where you're still on the length scale of the variation of the magnetic field, and then you don't see this hole anymore, f is equal to 1. And then if you zoom in and you look at this hole in f, then you don't see any variation in magnetic field, because you're just looking right at the top of this picture here. So you have two expansions depending on whether you're on this scale, on the order 1 scale, or whether you're on this scale, which is the 1 over kappa scale. So I sort of said earlier that I'm going to choose the penetration depth as my length scale. So here, I'm on the penetration depth. When I zoom in with 1 over kappa here, that means I'm going back to look at the coherence length as my length scale. So I'm choosing the length scale for variations in f in order to measure distance. So let me just show you briefly how that goes. So for large values of this Ginsburg-Landau parameter, you expect that f is going to be 1, which is its value at infinity, except in a small region near the origin, which is really the core of this vortex. So if you postulate an expansion in which you go up in inverse powers of kappa, and I'm going to label this outer expansion away from the core of the vortex with a little o, and then we'll do an inner expansion, I'll label that with I. So you can postulate this expansion and substitute it into the equations, and then equate coefficients of different powers of 1 over kappa. And then at leading order, you find you get a simpler equation. And what you find is that exactly as you'd sort of anticipated by looking at the picture, you find the magnetic field is 0, and the potential is 0, and f is just 1. So the thing just looks superconducting away from the vortex core. You might have expected to say, well, why didn't I get any magnetic field here? But in fact, if you remember, the flux quantum is order 1 over kappa. So the field comes in a little bit further down the expansion. So it's not this term which is generating the magnetic field. It's this term here, because the quantum is actually 1 over kappa, not order 1. Okay, so then if I go and look what's happening right near the vortex core, then the way you do that is you rescale length with 1 over kappa. So I'm going to call my rescale length is going to be capital R. So when capital R is order 1, little r is order 1 over kappa, that means I'm really looking at the variation of f near the origin. So you do this rescaling, and that's what the equations become. So you can now see that I've got a 1 here, but the kappa squared has come into this equation. So instead of a 1 over kappa squared here and a 1 here, I've got a 1 in this equation and a kappa squared here. And now you say, well, let me expand the solution in inverse powers of kappa here in the inner region. And so at leading order, I get something non-trivial up here now. But down here, this term completely dominates this term, so I just get the left-hand side here. And f and a should be bounded at the origin. And in order to match with the outer expansion that I found, I need that a goes to 0 at infinity and f goes to 1 at infinity. And so again, you find that the magnetic field is still 0 at this order in the inner region, but you get a non-trivial solution for f, which I think is exactly the equation that Evelyn wrote down this morning. And in fact, so I'm doing this for a steady rectilinear vortex, but in fact, we'll see tomorrow that even in more general cases, this is always the structure of a vortex core. So even if you have moving vortices, curved vortices, when you get in and really look closely, At leading order, they all look the same like this. And you can show again that there's a unique solution to these equations. All right, so now I know what the vortex core looks like. I still don't know what the outer magnetic field looks like because I've got to go a little bit further down the expansion away from the vortex core to see how this vortex is generating magnetic field. So if I look at the 1 over kappa coefficient, the coefficient of 1 over kappa in the outer expansion, so I'm going to the next term in the equations. So remembering that the leading order solution was F naught is equal to 1, I find that the next term in the expansion, this F1, is just 0. So in fact, F is going up in inverse powers of 1 over kappa squared rather than 1 over kappa. So it's 1 plus 1 over kappa squared, etc. And now finally I get something non-trivial for the magnetic field. So this equation for A1, this phase term, the minus n over r, which has come from the fact that I chose the phase of the order parameter to be e to the I n theta. So that n has finally made it into the expansion. So I now need to look at the solution to this equation, and the solution which decays at infinity and has the right behavior as I match towards r is equal to 0 is this one here. So A1 is n over r, and then K1 is a modified Bessel function. And from that I can work out the magnetic field, and the magnetic field is, well, it's this thing inside the bracket here. And when you apply that to this solution, you find that it's just K0, the other modified Bessel function. So I've now got an expansion for F inside the vortex core, and I've got a good idea of what the magnetic field is doing away from the vortex. And in fact, so I'm going to show one more term. Yeah, so I said F goes up in powers of 1 over kappa squared. If you go to the next order, you can work out what the correction to F is. So leading order, it's just equal to 1. It only actually really gets to 1 at infinity, so the correction term is minus n squared times kappa 1 squared. It's given by this expression. So by postulating this separation of length scales, it enables you to make asymptotic approximations to the solutions to these equations, depending on whether you're away from the vortex core or whether you're in the vortex core. And that enables you to do all sorts of things. So tomorrow I'm going to use that to look at deriving law of motion for how these vortices move. So for a fluid vortex, we saw in the morning that a fluid vortex is convected with the fluid. It's not clear what's the law of motion for a superconducting vortex. So I'm going to show you how you can derive that using this idea of inner and outer expansions tomorrow. But the other thing we can do with this is to say, when I started off with type 1 superconductors, we said, all right, what's the critical field? If I look at the Ginsburg-Landau energy, and I balance the energy of the normal state and the energy of the superconducting state, if I make them equal, then that tells me the critical field at which the minimum switches from one to the other. So I can do the same thing here now. So we've already said that if you're at low enough magnetic field, you should be superconducting. But for high magnetic fields, you should go into the mixed state. So what does that mean? It means you start to get vortices in there. So the magnetic field at which that will first happen is the energy at which is the field at which the energy of a single vortex is equal to the energy of having no vortex. Okay? And we can calculate that by working out what's the energy of this vortex solution. So we've got the Ginsburg-Landau energy. For the transition region, we took the solution and we substituted it into the integral and evaluated what we got. We can do the same thing now with this vortex solution. We take this approximate solution we've got and we substitute it into the Ginsburg-Landau energy. So this is the solution we've found so far. If I'm away from the vortex core, I've got magnetic field, vector potential, and order parameter. Everything is known about this. These Bessel functions we're all familiar with. In the inner region, then you find I've got this core, this sort of universal function which describes what the core looks like. I have to solve a differential equation to find this, so I don't know it explicitly. And I've got a corresponding, I know the vector potential starts at 1 over kappa squared in the inner region. So if I want to calculate the energy now using this expansion, so the energy of a vortex minus the energy of the superconducting state, and this is the last calculation I'm going to do. This is the Ginsburg-Landau free energy written down for this particular form of the radial solution. So I've used the fact that F is only a function of R and A is only a function of R. And again, by manipulating this energy using the equations, I can reduce this long expression down to just a couple of terms here. So now if I use the asymptotic expansion of the previous section in here, then, well, so I've got, it's a little bit more tricky than just substituting the expansion in, because I've got one expansion which holds if I'm not too close to the origin, and one which holds if I am close to the origin. So, and this range of integration here goes from 0 to infinity. So what I have to do is to split this range of integration at somewhere, I've called it delta. So I integrate from 0 to delta and delta to infinity. And I'm going to choose delta to be in between my two scales, so that 1 over kappa is the size of the core, and order 1 is the size of the outer region. I'm going to choose this delta to be in between. So that means that in this integral here, delta is much bigger than the core, so I can use the outer expansion. And in this region here, delta is small, so I can use the inner expansion. Okay, so I split the range of integration sort of in the middle of my two expansions, so that in this bit I can use the inner, and in this bit I can use the outer. So in this integral here, I change variable, and I write it as a function of this inner variable, capital R. And then I can substitute the inner expansion into it. And in this integral here, I just use the outer expansion. So then, now I've substituted in my expansion as a function of kappa. So here I've just written it in terms of capital R. That got me an Fi. Then I expand this Fi in powers of 1 over kappa. So that gets me to the leading term is the Fi 0. And likewise here, well, we found that F in the outer region is 1 plus 1 over kappa squared. So the first term in this expansion is the F2 term. That's why I needed to go as far as F2. And we found F2 was just this modified Bessel function. In fact, you can do that integral exactly, and it gives you this term here. This one here I can't do exactly, but I have to do a little bit with it before I can make it a finite integral. You can see that this log delta is appearing here, but the answer shouldn't depend on delta, because I could choose delta to be whatever I wanted. So there must be a log delta coming from this guy as well, and indeed there is. If you look at how F behaves as you go to infinity, you find it's 1 minus n over r squared, and that means this guy here is going like 1 over r squared. So when you multiply by that r, you get a 1 over r. So the upper limit here is giving you a log again, and that's going to give you a log delta, which cancels with the log delta that I get from the other one. So I've got a logarithmic singularity here because of this behavior. So the neat way of dealing with that is to just subtract off this this n over r squared, and then whatever you've got left decays sufficiently quickly that the integral exists, and you can let the upper limit go to infinity. The problem with just doing that is that this thing is all right at infinity, but it's not all right at the origin. So I can't just subtract it off the whole range, so it's a little bit messy. What I first do is integrate from 0 to 1, and then 1 to delta kappa. Then this guy is just a finite integral that I can do numerically. For this 1 to kappa, I can't let this delta go to infinity, this delta kappa go to infinity, because this has got a logarithmic singularity. So I subtract off minus n squared over r squared, and I add it back on again. And then this guy here now is decays sufficiently rapidly at infinity that in the limit as delta kappa goes to infinity, this just becomes a number. That's all right. And this guy I can do explicitly, and it gives me the log delta kappa. So for large delta kappa, this is the dominant term, in fact. It looks like a log, but everything here then is order 1. So the upshot of all that manipulation was that this first term in part of the integral has got a log kappa over kappa squared, and then some constant over kappa squared. And if you want to know what the constant is, you just do this integral. Right, that's a bit more messy than you would have liked, but it's not too bad. You can do the other part of the integral very easily. And so in the end, you find this energy that you get has got this expansion for large kappa. So it looks like log kappa over kappa squared, and then there's some constant over kappa squared. And crucially, there's a sort of minus h applied over kappa here. So there are a number of things that you can observe from this energy. So the first thing is that the winding number appears like n squared. So first of all, that tells you plus and minus vortices have the same energy, so you might have expected that. That's all right. It tells you that an index 2 vortex has 4 times the energy of 2 index 1 vortices. And so that tells you that it's not energetically favorable to have a vortex with a winding number of 2. It'd be much better to have 2 with winding numbers of 1. Okay? So already from this, you can see that you're not expecting to find any vortices stable with indices greater than 1. Or either it should be plus 1 or minus 1. I mean, this is a steady theory, so that's just telling you that they're not energy minimizers. It doesn't tell you necessarily that they're unstable in a dynamic theory, but they are. The other thing you can do is say, all right, suppose I put n is equal to 1, if h is small, then this E is positive, and if h is large, then this E is negative. And what that tells you is that the energy of the vortex solution becomes more favorable when h passes through a critical value. And to find that critical value, you just set this thing equal to 0. Remember, this is the difference between the energy of the vortex and the energy of the superconducting state. So if you set this equal to 0, you get this expression for what this lower critical field is, and you find that it's log kappa divided by kappa at leading order, and then there's some 1 over kappa correction. I have a feeling that next week Leo Bronsart might talk a little bit more about energies of isolated superconducting vortices. So you might see this log kappa come up again there. All right, that's all I wanted to talk about today. I've sort of got you familiar with where vortices came from and how they were really a side effect of the Ginsburg-Landau theory. It was not designed for them. They came out as a sort of byproduct. But it turns out they've turned out to be rather important. We've seen that you have this mixed state where you have a lot of vortices messing around inside the superconductor. I haven't shown you what the upper critical field is. I'm not going to. We've seen what the lower critical field is. But most of the time, what we're going to do for the rest of the course is look at vortices, superconductors in the mixed state, and we'll have a collection of isolated vortices which will actually be well separated. So when you get to the upper critical field, the cores of the vortices start overlapping with each other. We're going to be sort of above the lower critical field, but not too close to the upper critical field, so that we can consider that vortices are isolated. They interact through the magnetic field, but not through the core. So they're separated on distances much greater than 1 over kappa. As I said, tomorrow we'll mainly do rectilinear vortices, and then on Friday we'll do some vortex filaments. Okay, thanks for your attention.